so here we're going to give you a general outline of Part G on the permutation group's adventure sheet, which is to prove that a permutation is either odd or even, that it can't be both. That there isn't, if I can write it as an even number of, a product of an even number of transpositions, that maybe Ava can write it as an odd number of transpositions. We're trying to prove that that can't happen. So we're going to give you an outline of this proof rather than step-by-step walking through Part G. We're just going to give you an idea of how it works. So the idea here is to think of permutations, and maybe let's say Sn, these are permutations, as permutation matrices. Now, what is a permutation matrix? A permutation matrix is a matrix with 1, 1 in each column and 1, 1 in each row, and all the other entries are zeros. 1, 1, 1, 1 in each column and row, and all others are zeros. All other entries are zeros. So Ava's going to help us see this in practice, looking at S3 and writing each of the elements of S3 as a permutation matrix.
Okay, so the way that you do this is, well, you're going to have 3 columns and 3 rows, and you want to first use your column, say is 1, 2, 3, and 1, 2, 3, and you want to label 1 in the place where your column goes to the row. So, okay, the identity 1 goes to 1, 2 goes to 2, and 3 goes to 3, so those are the ones, and the rest are 0. Which, good, the identity in S3 corresponds to the identity in the matrices. 1, 2, well, 1 goes to 2, so the first column, the only non-zero entry will be in the second row. 2 goes to 1, so it'll be something like this, and 3 remains untouched, so 3 goes to 3, something like this. 1 goes to 3 will be this, so let me speed things up a little. 2 remains untouched, and 3 goes to 1, 2, 3, similar thing, so 1 remains untouched, and then 2, 3 get permuted. 1, 2, 3. Okay, this one's a little more interesting. So 1 goes to 2, so this is our first column. 2 goes to 3, so this is our second column. And 3 goes to 1, so 1, 0, 0. And similarly, 1, 3, 2, 1 goes to 3, 3 goes to 2, and 2 goes to 1. And we can check that we only have 1 non-zero entry per row and column, and that non-zero entry is a 1. So that agrees with what Becca said.
And it's maybe not obvious, but you can convince yourself that these are all possible 3x3 permutation matrices. These are the only ways of satisfying this rule of only having 1, 1 in each row and 1, 1 in each column.
Mm-hmm.
Okay, so this is how we get this correspondence between permutations and permutation matrices. As a subset of permutations, we have transpositions. And these are in correspondence with, let's call them transposition matrices. And transposition matrices will be the matrices where they're the identity except that 2 entries are interchanged. So here, this is the identity on 3, but 1 and 2 are swapped. If I had a 4x4 version of it, it would be 1 and 2 are swapped. Oops. And it's the identity on 3 and 4. So a transposition matrix just means I swapped 2 of the ones of the identity matrix. And so what we'll look at now is the determinant. So because Ava, you had
No,
something to say?
I just wanted to
Gotcha.
say that that's the ones that I have highlighted here.
Great, thanks. So if we look at the determinants now, we know that every matrix only has one determinant. This will be a key fact. And we can use whatever method of calculating determinants that we want to believe this fact, but maybe the easiest was the method of patterns that we learned in 217. So to calculate a determinant of one of these permutation matrices, we observe that there's only one non-zero pattern. So maybe Ava will show us on 1-2
So
what that
pattern
pattern is.
was a combination of, well, the product of elements where you only took one element from each column and each row. So what Becca means by one non-zero pattern is that, you know, if I take this element, then everything that I multiply it to is going to be 0. So the only way of getting a product of elements where each element corresponds to one row and one column, in this case, is if you take these 3, the ones, and the way that you computed this determinant is that it had the sign, so the determinant of something like this is -1 to the number of lines going this way. So, I mean, in this case, there's only 1. So the determinant of this is -1. In this case, there are 3. 1, 2, 3. So the determinant is -1 to 3, -1. In this case, there's just 1. So the determinant is -1 again.
Yeah, so because these, and by the way, this is true of the permutation of the non-transposition matrices as well, that there's only one non-zero pattern. However, in those cases, there are 2 lines that go that way, whatever that way means. But in all cases, we can calculate the determinant by pattern, and there's only one non-zero pattern, and all the entries are 1s or -1s. So the determinant of any permutation matrix, oops, maybe I should do this in a different color. The determinant is always equal to either 1 or -1. But if we only interchange the 2 entries, the determinant of a transposition matrix is always going to be -1. But we also know that every element of Sn can be written as a product of transpositions. Which means every permutation matrix can be written as a product of transposition matrices.
Because this correspondence is going to be a group isomorphism. So, you know, if you have products here, they will translate to products here, and that's why you can make this analogy.
Yep. Moreover, determinant is a homomorphism. The determinant function is a homomorphism on matrices, which means if I take a permutation matrix and I write it as a product of transposition matrices, the determinant that I get is a product of -1s. And so my permutation matrix will have determinant 1 if it was a product of an even number of minus 1s, and it will be minus 1 if it was a product of an odd number of minus 1s. And that's well defined. The determinant's well defined, therefore the number or the parity, the oddness or evenness of the number of transposition matrices that I multiplied by to get a permutation matrix is either odd or it's even. There's no way to have a matrix that can be written as an odd number and separately an even number of transposition matrices. So the same thing translates to the corresponding permutations. There's detail, we didn't do any details here. There's details in the solution key, but we wanted to give an overview of how to think about it.
Mm-hmm. Cool.